Hello ROS developers and welcome to this live class number 102. My name is Alberto Ezquerro and today we are going to be talking about forward kinematics of robotic arms. So let's start. Alright, so hello everybody and welcome again to this live class number 102. As I've just said 1 minute ago, today we are going to be doing this live class on forward kinematics of robotic arms. So we are going to be checking a little bit how forward kinematics work from the theoretical point of view, a little bit, not too deep into that, and also how to deal with that in ROS in this case. So yeah, first of all, let me know if everything is fine. Can you see the image properly? The audio is good. Let me know in the chat so that I can keep going without issues. So hello everybody, I can see here Aryaman Patel, August Karaman, Lagan Kapoor, Wayne Fordis, Jasir Chacha Paramban. Well, that's a hard surname, let me tell you, Jasir. Hello. Engineering Nations, as always, you don't miss any live class. I like it. Alright, so thank you very much, guys, for being here with me one more time. So let's not lose any more time and start straightforward. So as always, first of all, I'm going to share with you the project. It might happen that you already have the project from last live class. Okay, in any case, I'm going to share it again here. So right now I'm going to just have, as always, going to get my energies. I'm going to have a drink of coffee here from my super fancy ROS developers Mac. There we go. And now yes, let's start. So let's go to the computer screen. And here I'm going to get my project and share it with you guys. So let me grab here the link and paste it here in the chat. There we go. Okay, so as always, once you click on the link, you are going to be taken into the ROS Development Studio, as I am. So if you are already logged in, you are going to get this project, this one here for live class number 102, into your workspace, into your My Projects section. In case you are not logged in, you are going to have to log in, and in case you don't have an account, you are going to have to create an account. Just create it. It will take you a few seconds and it's completely free. So once you get the project, you are going to be ready to go. Yes, so okay, so in case you already have this project from the previous week, it might happen that you see an icon, a button like this one, which says this fork is outdated. Click here to get the latest version. Yeah, so in case you already have this project in your workspace, you can click on this button. Yes, in this button that it's going to appear in your version of the project, and then you're going to get the latest version. Yes, so once you have the latest version, just click on the open button and open project, and this is going to start opening the environment for today's live class. Yep, as always. So meanwhile, this loads. This might take a couple of minutes depending on connection and different things. So meanwhile this loads, let's keep talking as I always do. So today we are going to do the live class on robotic arm kinematics, because or as a preview of the course that we are going to be publishing very soon in our academy on basic kinematics for manipulator arms, for robotic arms, whatever. So this is part of a series that we are publishing into our academy, which, by the way, you can come here by clicking on the ROS courses button. This is going to take you to our academy, Probably most of you already know about it, but for the new ones, I want to introduce you to our academy. So today we are going to be talking on kinematics of robotic arms, because very soon we are going to be publishing a course on robotic arm kinematics. Yes, today we are going to focus on forward kinematics, but in the course we are going to have more contents, like for instance inverse kinematics, which are super important as well. Yes. Then not only this, but in the following days, weeks, let me tell you that we are going to be publishing some other super interesting new courses, like for instance basic dynamics of robotic systems, super interesting course. Also we are preparing another course on navigation with ROS 2, also another course on Kalman filters, for instance. So stay tuned, and there are going to be more surprises very soon, which I cannot reveal yet, but just stay tuned. And for this live class and for the previous ones and the future ones, what we are going to be doing is to do the live class as a teaser of new courses that are going to be coming to the academy. Yes, so today it's a teaser of the robotic arm kinematics. And in the following weeks, I don't know, maybe in next weeks we are going to do a live class on Kalman filters, I don't know, yes? But I just want you to tell you this, that stay tuned, because there are going to be coming new things, new super interesting things to the academy, so stay tuned. So, alright, then let's come back here. This should be already loaded. There we go. So, here we have the notebook, which is automatically opened. Yes, so make sure that your notebook opens with the proper notebook. In this case, it's the ROS Developers Live Class number 102. Yes, and yes, so just here a couple of prerequisites that you should have in order to properly follow this live class. In this case, it's to have a basic knowledge of Linux and a basic knowledge of Python. So in this case, both of them you can complete these courses completely for free in our academy. We have both of them here. In this case, we have the Python 3 for robotics, which is completely free. So in case you want in case you don't know anything about Python, this course is going to be perfect for you. And in case you want to test your skills or improve them, whatever, you can also have a look at this course. It's completely free, as I say, and the same for the Linux one, and these two. So if you want to become a ROS developer or work as a robotics developer, these two skills are mandatory for you, let me tell you. So you are going to have to know basic concepts of Linux systems, and also you are going to have to know how to program with Python. Yep. All right. So next thing to do, let's set up the environment. So today we're going to be working with a simulation. Yes, in this case it's a manipulator arm, a super nice and cool manipulator arm, which has been developed by the guys of the Clarkson University. So let me give them a shout out. Yes, so in order to start the simulation, all we need to do is to open here the simulations menu, click on the choose launch file, and then we are going to select the Clarkson_om_gazebo.launch file from the ASM URDF10 description package. So let's come here, click on the choose launch file button, and here under the ASM URDF10 description package we select the Clarkson OM Gazebo launch. So I'm going to select this launch file and click on the launch button, and this is going to automatically open here a Gazebo window, as you can see, and it's going to start loading my Gazebo simulation. Yes, so in this case we are going to be working with this manipulator, which is a custom version of the Open Manipulator that, as I have said, has been developed by the guys of the Clarkson University. And we are going to use this manipulator in order to practice today with Forward Kinematics. So let's see, here I have my simulation loaded. Excellent. Okay, so at this point I would like you all guys to be at the same point as I am. Yes, so here with the notebook opened at one side and the Gazebo simulation opened at the other one. So this way we are going to be ready to start working on the live class. Yes, so let me know, guys, if everything is okay. You have the gazebo simulation loaded, the notebook prepared, so that we can start. Let me have a quick look here at the chat. Everything is good. I'm ready, says Jan Spice. Works great. Ready, says Madhav Rawal there, with a lot of enthusiasm. I liked that attitude. Yep, mine is up. I'm ready. Okay, great. So let's go for it then. Everybody is ready and set up, so let's go for it. Then, first of all, what is forward kinematics? Yes, so we know as forward kinematics the use of kinematic equations of a robot in order to compute the position of the end effector of the manipulator from specified values for the joint parameters. Yes, so some basic concepts that you need to know. So, as you know, robotic arms or manipulators are composed of joints, links, yes, and in this case the final link, which in this case it's this one, it is known as the end effector or gripper also. Yes, this could be, there are many different types of grippers. In this case here we have a parallel gripper. It can be a hand-like gripper, whatever, yes, but the last link, the one that we use to grasp objects with the manipulator, it is known as the end effector. Yes, so what is forward kinematics? Well, forward kinematics is the use of the kinematic equations, the use of equations of our robot in order to know what is the position of this end effector. But in this case, it is knowing the joint parameters. Yes, so if we know the position of all the joints of our robot, then we can calculate the position of our end effector. Yes, so this is what we know as forward kinematics. Yes, so given a kinematic chain composed of links and joints with multiple degrees of freedom, finding the position and orientation of the end effector in the workspace when all the joint parameters are known. This is called forward kinematics. Yes? Then, okay, so in order to know the forward kinematics of our robot, what do we need to do? Well, we need to follow several steps. Yes, we are going to first talk from the theoretical point of view, and then we are going to move to ROS. So, the first thing we should do, if we want to calculate the forward kinematics of our manipulator robot, in our case from this manipulator, the one we have here, the first thing I would do is to create a kinematic diagram of the robot. Yes? So what it is? What's this? What's a kinematic diagram? Well, a kinematic diagram is the representation of the connectivity of the links and joints of the robot. Yes, so all the links and joints of our robot are connected in a certain way. Yes, then the kinematic diagram is going to define how the links and joints of our manipulators are connected. Yes, then there are several ways in how to do kinematic diagrams, but the most common one is to represent the joints as cylinders, as you can see here in this image, and the links as lines. Yes. So here we have the joints represented as cylinders and the links as lines. Yes, then here we have the frames, etc. Yes, as I've said, I'm not going to go too deep into the theoretical part because it would take too much time. But all this is going to be better explained and more in depth explained in the course that we are going to publish in the academy. But today I cannot go too deep, so don't worry if there are some things that you don't understand completely. Just keep going, because at the end I'm going to try to make everything have a sense yes, when we reach the ROS part and the ROS practice. Then, okay, so the first thing would be to create a kinematic diagram of the robot, yes, which will represent the connectivity of our robot, the connectivity of the links and joints of our manipulator, yes. Then, also, this kinematic diagram is going to help us define or set the DH parameters. What are the DH parameters? Have you heard about them? So DH parameters are the Denavit-Hartenberg parameters. Yes. Then this is very known in the world of robotic arms manipulators. Yes. Then basically, so since kinematics operate by a series of transforms from link to link, if the robot can be described with relationships from link to link, then this could help solve the problems of getting the equations of our robot. Yes. Then basically the DH parameters are a description, are a way of describing a robot kinematically by giving 4 parameters for each link. Yes? So, well, first of all, I guess all of you know the difference between links and joints. In case not, let me just do a quick explanation, a basic explanation. So basically the links are the rigid parts, like these ones, are rigid parts, which connect the joints, yes? Then the joints are the parts that connect the links and which allow the motion of the robotic arm. Yes, we are going to do some tests later with the ROS part, so just keep going. Then basically the DH parameters are 4 parameters, which we have here, A, alpha, D, and Z, that are going to allow me to describe my robot kinematically. Yes? So, for instance, the parameter A is going to be the length of the common normal. So, assuming a revolute joint, which is our case, this is the radius about the previous Z. Yes? So, this sounds super strange, I know, but I'm going to show you now an example that hopefully is going to help understand this a little bit better. So, this is understanding the DH parameters is not an easy task, I can tell you. But, well, we are going to see an example here that maybe is going to help you understand a little bit better. However, in one live class, it's going to be hard to fully understand this, yes? But basically, just get this idea. So the DH parameters are 4 parameters that are going to allow me to describe my manipulator arm in a kinematic way, yes? It's going to be 4 parameters that I'm going to assign to each of the links of the robot. Yes, then we have the alpha, which is the angle about the common normal, the D, which is the offset along the previous Z to the common normal, and Z, which is the angle about previous Z from old X to new X. Yes, so this sounds super strange, so let's just try this demonstration, which is going to allow you to test a little bit this. So now just come here, select this cell that we have here, select it, just clicking, left click on this cell, and then click on the run button, yes? Then this is going to open a live demo from Wolfram, which is super interesting, and allows us to test these parameters in order to try to understand them better. This is loading. Alright, so as you can see here, we have a 3 joint manipulator, super basic, 3 joint manipulator with 3 joints, which we can configure the joints to be either revolute or prismatic. In this case, we are going to set it to revolute because our robot has revolute joints. So now, as you can see here, we have 4 parameters, the Z, the D, the R, and the alpha. Yes, the R, in this case, it's named R, but this is the equivalent to the parameter that here we have introduced as A. Yes, take this into mind. Then here, this allows us to change these values and see live how this affects. Yes, so for instance, if I am decreasing the D, we can see that joint 1 is getting closer to joint 2. As I increase the D, we can see that joint 2 is getting far away to joint D. So basically we can see that this D parameter refers to the distance between joint 1 and joint 2. Yes, we have the alpha as well, which we can modify here. Yes, the R, which is the equivalent to the A parameter in this case. As you can see here, what is happening is that joint 2 it's rotating basically. Yes, let me change it here a little bit. There we go. Yes, and the same goes for the A parameter. Yes, so if I modify it, I can see how this affects directly. Yes, so here we can see that this is an offset from the previous Z. Yes, it's an offset from this joint to the previous Z. Yeah, makes sense. So if I have it at 0, joint 2 is directly up here from joint 1. It's in the same line of the Z-axis of the previous joint. If I move it, I can see that here it appears an offset. Yes? Alright. Anyways, just you can try some things, modifying the parameters from the different joints, and this is going to help you understand a little bit better what each parameter refers. Yes? Then these parameters are going to represent a relationship between each of the links. Yes? So, okay, then let's keep going. So, in order to create our kinematic diagram, remember, yes, the first thing, one of the first things we should do is to set up the axis of each of the joints. Yes? Then in order to set up the axis, we are going to do it very simple. So, the Z-axis will be on the axis of rotation for a revolute joint. We have revolute joints, so let's imagine. Okay, let me start doing some practice here. So let me launch here super quick RQT. Open our graphical tools here, move it to a new window. Okay. There we go. I am loading here the RQT tool, which is going to allow me to move here the joints of the robot with a graphical tool. So let me open here the robot tools and the joint trajectory controller. There we go. All right, so let me connect now here to the controller, which is the arm. I'm going to turn it on. Okay, so here with these sliders now I can change the position of the joints. So let me change the position of the ID 1 here super quick. Let me change it here, and as you can see, this is making the joint 1, which is named, by the way, ID1, rotate in this case. Yes, now it has rotated to one side. If I move it now here to this side, it's going to rotate to the other, as you can see live. Yes, so basically the joint is revoluting around its Z-axis. So basically this rotation tells me that the Z-axis in this case it's in this direction. Yes, it's facing it's like in the up direction. Yes, like we can see here. Yes, so like here we have the Z-axis in this direction, which is the case of this. Why? Well, I can see this clearly because if I rotate this joint, I can see that it's rotating along the z-axis. Yeah? Make sense? All right. Then basically with this in mind, we can set the x-axis and the y-axis using the right-hand rule. Yeah? Which we have here. Probably most of you know, super famous rule in order to set the axis. Yes? All right. Then having all this in mind, we can create the kinematic diagram for our robot. Yeah, so in this case here I have the z-axis, which we have defined, it's in this direction, and then we have set arbitrarily, in this case, the x and y axis. Yes, using the right hand rule in this case. Yes, so applying this to each of the joints, we can get the following kinematic diagram that we have here. Yes, we can see here that we have all the joints represented as cylinders here, with the axis set for each of them depending on the rotation. So for instance, here in joint 2 we can see that the z-axis, which is the blue one, it's not in the up direction. Why? Well, because if I come here and move this one, let me move it a little bit, we can see that the rotation is different. Yes, so it's rotating around a different z-axis, which in this case it would be in this direction. Yes, let me move it on the other one to see it better. See, so you can see that the rotation in one case it was like this, and in this case it is like this. Yes, we can see here the rotation, we can see it here represented as the zeta value. Yes, here's the z1, z2, the frames, and the d parameters, which as we can see are the distance between the different joints, as we have seen previously in this demo. Yeah. All right, so here we have a kinematic diagram of our manipulator. Yes, with the frames, the z's, the d's, etc. Yes, what happens? Well, in this case, this kinematic diagram, it's not ideal in order to use the DH parameters. So as you can see, in this case, we don't have any offset between the links, so we don't have any A parameter, for instance. Yes? Remember the A parameter that we introduced here, that represented the offset here. You will see this is going to move here to the right now. There we go. Yes, so in this case this is the A parameter. So in this case we have all the joints lined up, so we don't have any offset, so we don't have any A parameters. So this is going to make us very hard to use the DH parameters. So what can we do? Well, in this case what we're going to do is to modify the kinematic diagram in order to make it easier to introduce the DH parameters, so that we can use them. Yes? Okay, so this is a bit complex, I know, I'm aware of that, but I'm going to just keep going, and later you can review it if you want and try to grasp better the concept. Yes, because otherwise this is going to take too much time. So in this case I'm going to do some modifications to this kinematic diagram in order to better fit the DH parameters. Yes, so here we have the modified kinematic diagram in this case. Yes, so as you can see we have applied rotations to some of the joints. Yes, here we can see the offset. So previously we had the joint 3 here right up of joint 2, so now we have modified this, we have moved it here, so this introduces an offset, of course, which is the A parameter. Yes, we have seen that we have applied some rotations to the joints as well. Yes, so why this kinematic diagram? Well, just in order to make easier to introduce the DH parameters into my kinematic equations. Yes, just keep this in mind. We can do this. Yes, we can set up the kinematic diagram so that it's going to make easier later the calculation of all the kinematic equations. Yes, here in this case, for instance, one of the rules we are using is this one. when a reference frame that has its z-axis running through the center of the next frame, it can be moved along the z-axis without any resulting change in the description of motion. So as you can see, this is basically what we have done here. For instance, since the z-axis goes along the center of the reference frame of the next joints, basically we have unified here, we have moved the frames in order to put them all together here. Yes? Okay. I'm not going to go too deep into this because it might be too hard right now. So let's just keep going. Just keep in mind that here we have created the kinematic diagram for our manipulator robot. Yes, which is this one in this case. Then let's keep going. So once we have here our robot configuration, we can define the DH table, which is this one, which is going to define the relationship between all the joints of our manipulator. Yes? So for instance, here we can see the joint 1, which has all its values to 0, and then we can see here joint 2, which already has a rotation applied to it of minus p half. Yes, this is the rotation that we have applied here. So we have rotated joint 2 this angle, yes, minus p half. Yes, then here we have other joints that we have also rotated with the rotations and the a parameter, which in this case it's between joint 2 and joint 3, as we can see here. Yes, so and d4 as well, of course. Okay, so having created the kinematic diagram, we can then generate the DH table, which we have here. Yes, so now here we have some explanations, as you can see. So joint 2 has been rotated minus 180 degrees, minus p half. Yes, you can see that we have also applied rotations to joints 4, 5, and 6. These rotations are represented in the DH table as the alpha of each joint. Yes, so let's keep going. Yes, so how it is going until this point. So I know all this might be a little bit too much right now, I know. So talking about kinematics, either forward kinematics, inverse kinematics, from a theoretical point of view, it's very hard, at least in 1 hour. So I'm trying to introduce some concepts, yes, and so that later it's going to be easier to follow up. But as I've said before, don't worry, it's normal that you don't understand this perfectly now, because it's impossible to explain all this properly in 15 minutes. So don't worry. Yes, just get the idea, and later you can, if you want, review this and get more information on, or later you can complete our course, which is going to have everything much more step by step. Yes. So, okay, once we have generated our kinematic diagram and once we have obtained our DH table, we can then generate we can calculate the forward kinematics. How? Well, let me have a quick look at the chat here. Yeah, so Wayne for this, it's pointing out Wayne Fordis is pointing out correctly that p half it's 90 degrees, not 180. That's totally true. Yeah, so here we have that minus p half it's 180. This is wrong. Yes, 180 degrees it's p, not p half. Yeah, so this is like this. Yes, thank you very much, Wayne, for pointing out this. No, it's not much hike. Please carry on, says Hassan. Good job. This is a great introduction. Thanks from the references, tables, and tools for us to explore. You're welcome, Gloria. Okay, so let's keep going. Let's keep going. All right, then. Okay, then once we have this, so using the DH table, the first reference frame is transformed to the second reference frame of the manipulator. Then the next and the next until the tool is reached. Yes. So since the DH notation parameterizes the relationship from a frame to another frame in terms exclusively with respect to X and Z translation and rotation, the transform from frame to frame can be related X rotation alpha, X translation A, Z rotation Z, and Z translation D. So the X translation and rotation from frame to frame can be described by the following matrix. Yes, so we can obtain the following matrix, which is going to relate one frame to the next one, in this case from the point of view of the translation in the x-axis. Yes, then from the point of view of the translation in the z-axis, we can obtain this other matrix, which is going to relate one joint to the next one. Yes, to the adjacent one. Then so now to construct the complete transform from frame I to frame I minus 1, which includes X and Z translation and rotation, we can multiply above these two matrices, which will result in the following matrix which we have here. Yes, so we have generated this matrix, which is going to relate frame E to frame I to frame I minus 1 from the point of view of the X translation, and we have generated this matrix, which is going to relate frame I to frame I minus 1 from the point of view of the translation in the Z-axis. Then by multiplying these two matrices, we can obtain the complete T transform from the frame I to the frame I minus 1. So you can see by multiplying these two transform, which is going to result in the following transform. Yes, so once we have this transform, we can then substitute the DH parameters that we have in our table into this transform, which is going to result in the following matrices. Yes, so we have here the transform matrix from frame 0 to frame 1. Then we have the following from frame 1 to frame 2, the following from frame 2 from frame 3, etc. Yes, being frame 6 the end effector. Yes, so from the base frame, which is 0, to the end effector, which is 6. Here we have all the transform, the resulting transform from frame to frame. Yes, then by multiplying all these transforms, we can obtain the transform from frame 0 to frame 6, which is going to relate the base frame of our robot to the end effector of our robot. Yes, then this is going to result in a matrix like this one. Then in this matrix, we can already obtain the position and orientation of our end effector. How? Where, as you can see, these values, the values R11, R12, R13, R21, 22, 23, and 31, 32, 23. So let me try to select them here. Yes, so these values, which are marked with here, are the rotation matrix, represent a rotation matrix. And here we would have the position in X, Y, and Z coordinates. Yes? More or less makes sense what I have just explained. Okay, so as I have just said, don't panic, don't worry. I know this is not easy to understand. Just try to get the general idea. So basically, we have started from the beginning here, creating the matrix, the matrices, then substituting in the matrices the DH parameters, and then finally constructing all the matrices that relate each frame, so that we can construct the final matrix that is going to relate frame 0 to frame 6, which is our end effector. Then with this final matrix, we can already obtain the position. We can obtain the rotation matrix of our end effector, which is going to give us the orientation, and we can also obtain, as we can see here, the position in the XYZ coordinates. Yes? So, as you can see, obtaining the forward kinematics from a theoretical point of view, from a mathematical point of view, it's not an easy task. Yes? It's not an easy task at all. So, Okay, let's stop right here, the theoretical section, and let's start with the ROS point of view. So what about ROS? Okay, so ROS provides us many tools in order to deal with robot kinematics so that we don't have to go through all of this. Yes? ROS, as always, it's coming to make our life easier. Yes? So, one of the things we have in ROS are the transforms, very known transform. Probably most of you, if you have already worked with ROS, know what transform are. Yes. So let's do a quick example. Let's launch here. Well, I can see that we already are quite. We have already spent much time. So let's try to go to the point here. Alright, so by defining our robot in a URDF model, we can publish, using the robot state publisher, we can publish the transforms of our robot. What are the transforms of our robot? Well, basically the transforms of our robot are pretty much the same as Forward Kinematics. So it's going to define a relationship between the joints and links of our robot. Yes, you can see them here. Then with this, let's start here with the practical exercises. So let's open a shell here, and first of all, let's execute these commands here. cd catkin workspace src, and let's execute this command. ROS run tf view frames. This command basically is going to generate the frames tree of our robot, in this case of our manipulator robot, in a PDF, so that we are going to be able to download it. Yes, so let me open the IDE right now. This is going to generate in our Catkin Workspace SRC folder this frames PDF file. So you can see here, Catkin Workspace SRC frames PDF. Yes, then if I can download now this file and open it here, and as we can see here, we can see the relations from the frames. Yes, here we have the world frame, which is related to a simulation, in this case to the simulated world. Then we have the base link, which is the base link is the base frame, which here it will be the frame 0. Yes, this 0 frame here, or here, this 0 frame would be this base link. Now you have link 1, link 2, link 3, 4, 5, 6, 7, and then we reach the grip link here. Yes? So as we can see, we have all the links of our robot connected. What does this mean? This means that since they are all connected, we can know the relation in translation and orientation from one link to another using the transforms that ROS already provides off the shell. If we properly create the URDF and publish the robot state publisher, we have access to these TFs, to these transforms. Yes? So, for instance, we can execute the following command that we have done here: ROS run tf echo link 1, link 2. In this case, let's execute this command. We are going to get the transform from link 1 to link 2, from this link to this link. So if I listen to the transform from link 1 to link 2, I'm going to get the following message, which, as you can see here, it's giving us the relation in terms of translation and rotation. Yes? So I can see here that the relation in translation is 0 in the x-axis, 0, 0, 6, 4 in the y-axis, and 0 in the z-axis. Then here I can see also the rotation. So this is giving me the relationship between link 1 and link 2. Yes? Then of course, since all of the links are connected, I can get the relation between any of the links and the gripper link. Yes? Make sense? So this is what we can do with ROS TFs. So as you can see, this is super cool and interesting from ROS. Yes, as always, making our life easier. Then Another tool we have, also off the shelf with ROS, we have the joint state publisher, which basically is going to give us the state of the joints of our robot. So if we do a ROS topic info of the joint states topic -1 to get only one message, sorry, the -n1 doesn't apply here, it's just for the ROS topic echo command. Okay, yeah, so ROS topic info joint states. So as we can see here, we have the publisher, which is Gazebo, and in this case we have the Robotics publisher subscribed to this topic, and basically into this topic we can do now, yes, a ROS topic echo, which you have the command down here, by the way, and we are going to see that basically into this topic we have the information of the joints of our robot. We have here all the joints, grip joint, the ID1, ID2, ID3, ID4, ID6, and here we have the information of the position of these joints. Yes, position, velocity, and effort. Yes, so basically using this topic, using the joint states topic, which is published by the joint state publisher, we can know the state, the data of all the joints of our robot. Yes, then knowing all the joints of our robot, remember from the definition of Forward Kinematics, knowing, let me go back here, so knowing when all the joint parameters are known, then we can calculate the position and orientation of the end effector. Basically this is Forward Kinematics, yes? So here we have a way, a super easy way, using ROS to obtain all the data of the joints of our robot. Yes? Then, what else do we have? Okay, so we have also access to Move It. Also, if you have worked with ROS, especially if you have worked with manipulator arms, with robot manipulators, you probably already have heard about Move It. Yes, Move It is the most important tool that provides many applications for working with manipulator robots. Yes, so in this case we are not going to go deep into Move It or how to create Move It packages. Here we already have a Move It package set up, configured and created for this robot, so we are going to just launch it. Yes, if you want to know more about Move It, how to create Move It package, etc., we have courses in our academy. For instance, the ROS manipulation in 5 days course, which is going to explain you all that. Here, what we are going to do is to just make use of it and launch it. So let's copy and paste this command here, which is going to start Move It for our robot. Yes. Then let me get a drink of coffee. 1 second. There we go. Right, so here we are launching Move It, starting Move It. Do I have something else running? Okay, I'm going to close now this RQT. There we go. I don't need it anymore. And this is going to open Move It here in the graphical tools window. We can see it. And here we can do many things. So basically we can send goals to the end effector of the robot in order to move it. In order to move, yes, here in the planning section. Yes, so for instance we can update here the position of the end effector by setting, in this case here I'm setting random goals, as you can see, yes, and I can calculate the inverse kinematics and calculate the path so that I can reach these goal positions, etc. Many things, yes. I'm not going to do this. However, there is a tool which is not so famous, but Move It provides and has this tool, which is the Compute Forward Kinematics service. Yes, so Move It provides this Compute F_FK service. Let's have a look at this service. If we do a ROS service info here, we can get more information of this service. This is a ROS service, yes, named Compute_FK. So the node that provides this service is Move Group. So this service is provided by Move It. yes? Then it uses this type of service message, get position fk, and it uses these arguments, header, fk link names, and robot states, yes? So we have also Moveit provides this service. And what does this service? Well, the name itself says it. So this service computes the forward kinematics of our robot, yeah? Then, what are we going to do next? Well, what we're going to do here in order to end the live class is to create a program that is going to compute the forward kinematics of our robot. Yes? Well, not exactly of our robot, but we're going to see it right now. Then, what do I need to know? Okay, I know I have this service. Then, if I want to use this service, I'm going to need to know how the message that the service uses works. In this case, is this get position fk. So, let me try to get some more information about this service message. So here, let me execute this, the ROS srv show command in order to get more information about this message. And you are going to see that the message is quite huge. It's very, 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 very big. Let's have a look here. And as any service message, it is divided into parts, the request part and the response part. Yes, every service message is divided into parts in ROS, the request and the response. So as for the request, we can divide it in three parts: the header, which basically contains of metadata about the message, like the timestamp, etc. Then we have the fk link names, which basically is going to it's the names of the link of our robot. And then we have the robot state. Yes, we can see that these three messages, the header here, the fk link names, and the robot state, are the three that are in the same level. So basically are the three main messages inside the request of this message. Yes, so we have the header, the fk link names, and the robot state. What is the robot state? Well, basically the robot state is the current state of the robot. Here we see that inside the robot state we have the joint state. So it is going to get the information, the current data of the joints of our robot. Why? Well, because we need the information of the joints in order to be able to compute the position and orientation of the end effector. Yes, this is forward kinematics. Yes, all right. So here we have the request part of the message. Yes, so basically the header, which is some metadata. We are going to need to provide also the names of the link of our robot, and we are going to need to provide the current state of the robot, especially the current state of the joints of the robot. We are going to need to provide this to the service so that it can calculate the forward kinematics, of course. Then if we go down here, we are going to see that here ends the request part of the message, and here starts the response. So as the response, the service is going to return me a pose stamped. A pose stamped containing the pose, which is position and orientation of, as you can see here, position and orientation of my end effector. Yes, so it's going to do the calculation and everything it needs, and then it's going to return me the position and orientation of the end effector of the robot. Yes. This is basically forward kinematics we have defined before, yes? So knowing the state, the current state of the joints, of all the joints of the robot, I can know the position and orientation of the end effector. This is forward kinematics. Then it's going to return me this pose for the end effector is going to return me a variable fk link names containing the names of the links of my robot, and finally it's going to return me an error code for Moveit. Yes, so has it worked correctly, success, has there been a failure, timed out, whatever. It's going to return me an error code. Yes, okay, so now I know a little bit better how this service message works. So now I'm more prepared to create a program that is going to use to call this compute fk service. Then let's go for it. So let me come back here to the notebook, and I'm going to create here a package where I will place my code. So let me copy and paste here this command. There we go. Let me first go to King Workspace SRC. Let me clear this. Okay, then inside the Kakin workspace SRC, I'm going to create my package, which I'm going to name ComputeFK, and I'm going to add ROS.py as a dependency. Yes, and this is going to generate this package here. As we can see here, this has generated this package, this empty package now, into my Kakin workspace. So now, inside the SRC folder, I'm going to create a new file, and I'm going to name it getfk.py. It's going to be a Python file. And finally, inside this file, I'm going to copy and paste the code I have here. Yes, so let me copy and paste the code I have here. Control C, Control V, and I'm going to paste the code here. All right. So let's have a quick look at the code that we have just pasted here. Yes. So as you, first of all, as always, we are doing some imports. We are importing ROS.py, some modules that we need. For instance, some messages. Here we are importing the robot state message, get position FK message, get position request. Yes, these are the messages related to the service that we want to call, this compute FK service. Then we are starting the node. We are initializing the move it commander. We are defining the move group commander, which in this case is arm. We are checking that we have actually running this compute FK service. And then we are creating the service client, the service proxy, to connect to this compute FK service right here. Yes, we connect to this compute FK service, specifying the message used by the service, which, as we have checked before, it's get position FK. Yes, makes sense? We remember? So ROS service info compute FK. Yes, it uses the get position FK message. Yeah. So we are connecting to this compute FK service using the get position FK message. Then we have to first generate the request part of this message. So as always, let me remember it, service, ROS services, ROS service messages have two parts, the request and the response. Yes. So first we need to fill the request, which, if you remember, the request, we checked it here before, it had basically three parts: the header, the robot state, and the FK link names. So basically, in order to generate the request, we are going to need to provide this information. And this is exactly what we are doing here. Yes? So we create the request part of the message, and then we fill first the header, which basically here, the only data we need to fill, the important data we need to fill is the frame ID, which is the world in this case. Let me pause 1 second to get a drink. And my throat is it's getting dry. I'm talking too much. All right. So I am here setting the frame which I am going to calculate. So the reference frame from which I'm going to calculate the position of the end effector in this case. Yes. So in this case, I'm doing it from the world frame, which is basically the base frame. Yes, it's the same as the base frame in this case. Yes. Then here I am providing the FK link names. So what is this? This is the name of the link that contains, that it's considered the end effector. Yes. So the link 6, it's the one that has the end effector of the robot in this case. Yeah. So let me open here the notebook. So link 6 basically it's the last link here before the end effector. Yes. So this is why we are going to calculate the forward kinematics to link 6 in this case. Yes, would be this one here to which the end effector is connected, the link to which the end effector is connected. And then where I was here, okay. Yes, okay, so I have specified the header information, in this case the frame ID. I have specified the FK link name, which is link 6. And finally, the only part remaining from the request I need to specify is the robot state. Yes, so in this case, here what I am doing is to define them as empty strings, empty strings, sorry, and here I am filling the information for each of the joint states. So here I am filling the joint state information with the name and position. Yes, here in this case I am hard coding this data. Yes, so as you can see here, I am setting the names with ID plus a number. Why? Well, because if I have a quick look here at the ROS topic echo joint states minus n1, I'm going to see that the names of my joints are ID1, ID2, ID3, and so on. Yes, so here basically I am iterating here in this while loop, and I am filling all the names with ID1, ID2, ID3, etc. And as for the position, I am setting the position of all the joints to 0.8. Yes, so I am hard coding the position because 0.8 it's not the real position of my robot. Yes, the real position information I have it here, as you can see. This is the real position of the joints of my robot. Yes, here in my program I am hard coding this position 0.8. Yes, then once I have filled the request part of the message, I have all the information, then I can call my service. Then once I call the service, I'm going to store the response into this variable, into this ROS variable, and in this case here I am going to print all this information. Yes, so this is basically the structure of this Python script. As you can see, it's pretty simple. Yes, then let's test it. So let's right now test it. First of all, let me make sure that the script has execution permissions, which it doesn't, so I'm going to give them chmod plus x to get fk, and then I'm going to run my program. So ROS run compute fk and get fk. There we go, only one time. Yeah, there we go. Okay, so I'm going to execute my program and let's see if this works and I get properly the response. Let's see. Okay, so I'm executing my program. There we go. And there we go. So here I have the compute fk. I have received the response from the service, and here it's providing me the pose information, the position and orientation of the end effector, giving this current joint state information. Yes? So what happens? Well, what happens here is that this joint information, it's not real. It's not the real information of this robot, as I have just said. Yes, this is hard-coded information. Yes? Because the position, it's not 0.8 for all the joints. This is false. Yes? So you can see the positions, we have them, we have the real position data here, published into the joint states topic. So what I want you to do as homework, is to modify this script so that you get the real information of the joint states from the joint states topic, and not like I have it here right now, which is hard-coded. Yes? Does it make sense? So this, I want you to do it by yourself as homework. Yes? So improve this script, modify it so that instead of setting all the joint positions to 0.8, we set them to the real position information, which is published here into the joint states topic. Yeah? So this is the homework I want you to do. And that's it. So yes, we have finished the live class. We are 10 minutes past the time we should have ended, but good job, mission completed. Yes, so thank you very much, guys. I hope you have enjoyed today's live class. Let me go back to my camera. Alright, guys, so yes, now you can see me, I think. Yes, there we go. Okay, yes. So yeah, that was all for today's live class. I hope you have liked it, you enjoyed it, you learned something new. And yes, keep in mind this. Remember that once this live class finishes, we are going to publish the whole video into YouTube as a regular video, so you are going to be able to review it, and from this point you are going to have this project in your workspace forever. Yes, so you can work on this project tomorrow if you want, next week, whatever, at your pace. Yes, you are going to have this project forever. Then thank you very much, guys. So I need to fasten. Let me. It was great. Thanks. Please do the inverse kinematics, says Hassan. Okay, maybe. I don't know. Maybe inverse kinematics are going to be inside the course. That's for sure. But maybe we are going to do them also in a live class in the future. Thank you for this in-depth look under the hood of Forward Kinematics with ROS. You're welcome, everybody. Thanks as always. Looking forward to the next class. Thank you very much. Good job. You're welcome, guys. Thank you very much for your kind comments. So yeah, thank you very much for being here with me. And take care. As always, as I say always to you, take care. And I will see you next week, next Tuesday, with the next live class 103. So thank you very much and bye bye. What are you doing, Alberto?
I'm training this intern with ROS.
Oof. Did you have the same experience? Spending too much time equipping your team with ROS skills? Check out our ROS Online training solution for enterprises, a fast and easy way to empower your team with ROS. From ROS basics to manipulation, perception, AI, ROS2, everything your team needs to learn is here. Practice with real and simulated robots. Train your team by doing from day one. Also, our ROS experts will provide you 1 hour of consulting services to boost your robotics projects. Want to become a happy Alberto? Request a demo today.